let's get into some springs. Old Hooke's Law. So we're going to be talking about these different springs, and did you know the different springs some can be really, really like hard to compress, and other ones are easy. Like, I don't know if you ever saw a slinky. That's a spring, but it's real easy to compress and stretch out. But maybe the suspension in your car is really stiff. So that spring's hard to compress. So there's different types of springs, and according to Hooke's Law, some of these springs follow some rules. So let's get into it. Hooke's Law. So here we go. We got a couple springs. And we're going to just say, let's move through. The force required to keep a spring compressed or stretched by some x units is written as F is equal to kx, where x is the distance, F, of course, is the force, and k is what we call the spring constant. Now, not all springs hold the Hooke's Law, but any spring we're going to discuss in this class will follow Hooke's Law. And I have it written down there where K is the spring constant, which measures the stiffness of the spring. But let's get into this. So a spring naturally will just stay somewhere, right? We're going to call that x equals 0. And this is our equilibrium point, where you don't have to push it, you don't have to pull it, you don't have to do anything to it. It's just going to sit where it is. Now, if we stretch the spring to a new distance, see, we're going from here to here, but our x is greater than 0, that's a stretch. So we'll say the positive distance is when you stretch it out. And when you compress it, your x is less than 0. But what's also true is when you stretch, your force is, when you stretch, your force is positive. When you compress, we think of the force as being negative. It doesn't really matter. When we're thinking negative, it's just the way we look at an XY graph. You know what I mean? Like, that's the negative direction, and that's the positive direction. So don't be getting too crazy. We're just talking about the direction. Somebody back in the day went, all right, let's just make it to where when we're stretching it, that's positive x's. When we're compressing it, that's negative x's. And you're going to find it doesn't matter too much as long as we stay consistent. Let's jump into what the formula is. Oh, look at that. That's what I was just talking about. When x is greater than 0, the force is greater than 0. We're moving in the positive direction. When the distance is less than 0, the force is less than 0. And here we are. We have a force function. This is our Hooke's Law right here. The force is that spring constant times x. What is W? And there we are. This is how we're going to find the work done to compress or to stretch a spring. Wow, I cannot speak today. It's nothing different from any other day, though. And that's it. That's your formula. From some distance from A to B. So I think it's probably best that we just start off and let's do an example. So we can see that this isn't that bad. It's not that bad. There are some tricks in there. You're going to need to know the difference between force and work. So let's read. It says, suppose, oh, there it is. A force of 10 newtons is required to stretch a spring 0.1 meters from its equilibrium position and hold it in that position. Now here it is, part A. Now on exams, I won't ask you part A. This is just for us to get started. This is almost always our first step whenever doing a Hooke's Law problem. So assuming the spring obeys Hooke's Law, because not all of them do, but in this class we'll assume it, we want to find the spring constant. Oh, here's our game. Force is equal to the spring constant times x. All right. So we're given some information. we're told what the force is, and we're told the distance, and that's x. So now you have 3 variables. You know the answer to 2 of them. I think that might be algebra. So I'm going to put in 10 newtons. Now, since I'm a math teacher, I don't write my units every time. That's chemistry. That's physics. And you're going to need to do that there. I'm just going to use the logic of it that I know that the spring constant is just going to be some k. I'm not even going to discuss the units. I don't care what the units are. I know how this formula is going to work. And you will too. All right. So we're looking for that k, and then we need to put in, 1/10, right? Now, do you get a calculator on your midterm? Or your test if you're an on-ground student? No. So I'm not going to write decimals unless you're super cool with this. Like, let me show you how that would work. We put it in, we're like 0.1. And now we say that our spring constant k is equal to 10 divided by 0.1. And I know everybody's better with decimals than they are with fractions, right? Right? Of course not. Of course not. Of course not. Yes, we understand money in that way. I'd much rather use 1/10. Now we look at it, you're like, I don't know, multiply by 10. So we find out our spring constant is equal to 100. Cool. We need that. That's always going to be our first step because we don't want force is equal to k times x. We want force is equal. We want the spring constant. So the force is equal to 100x. We need this in order for us to solve any other problems. Okay. So that was part A. Now let's talk about part B. We just needed that for us to do the rest. So let's do part B. Part B is asking how much work is needed to compress the spring 0.5 meters from its equilibrium position. So we have to think we're going to start at 0 and we're compressing it to negative 0.5. But this is your A and this is your B because we're going this direction. So when we go to find the work, it's equal to the integral of where you start. With Hooke's law, you're going to start at 0 unless it tells you something different. And we go to negative 0.5. Now we just take our force function, we pop it on in, and we do some work to it. I hate puns. I'm sorry about that. I'm sorry. So let's find the antiderivative. Oh, once again, I really don't like decimals. I really don't like decimals. 0.5 is the same thing as 1/2, and without a calculator, I think it's probably a good idea for us to do it this way. So we're going to see we have our, what's the antiderivative of 100x? Isn't that 50x squared? Yeah, that's 50x squared from 0 to negative 1/2. Now, do you think it's going to matter that we have a negative in there? You think that means anything? No, it's going to be squared. So it actually doesn't really matter whether you're compressing or you're stretching when it comes to the work. Work is just work is just work. So we get negative 1/2. We get 0. Yay, 0's the best. So we get 50 times 1/4. We get 50 over 4. And if you try and write a J after that, you're going to lose a point. Even numbers over even numbers are your teacher's biggest pet peeve. How about 25 over 2 joules? Now, if you want to, you can do extra work on this problem. You go right ahead. If you want to write down 12.5 joules, be my guest. It's fine. You can always write down. You can do more work. It's always up to you. I know a lot of students were like, no, I like more work. I have to know what that fraction is in decimals. I'm being facetious. All right, well, let's do C. We've done B. You know, my organization is pretty terrible, but I want to keep this thing up. So we have our work is equal to, and now we're going to do what? We're going to stretch the spring to 0.25 meters. So now our A is still 0, but now we're going to move this way to 0.25. That's going to be our new B. So we set up our integral. We go 0 to 0.25. You can use decimals if you want to. I'm not using decimals. dx. And what's dope is we already know the antiderivative, don't we? It's 50x squared from 0 to 1/4. So we get 50 times 1/4 squared minus 0. Sorry, I'm just writing that in. So we get 50 times 1/16. Or 25/8 joules. We found another answer. All right, and now for the trickier one. How much additional work is required to stretch the strings? Wow, I do speak English, I promise. How much additional work is required to stretch the spring 0.25 meters if it has already been stretched 0.1 meters from its equilibrium position? I'm actually going to jump off to the side and let's draw this. So we're starting at 0 and it says we're going to stretch it, but we were already 0.1 meters and we want to go 0.25 further. That would be 0.35. So we started here and we go to here. It's just changing our bounds of integration. So we're going to say that the work done for part D is equal to the integral of 1/10 up to 7/20. Oh, yeah, sorry about that. 0.35. But again, you use your decimals. You use your decimals. No problem. You can square 0.35 without a calculator, can't you? No big deal. Huh? So we take the antiderivative. I know it's going to come as a big shock. It's 50x squared. 7/20, or from 1/10 to 7/20. I'm going to do it this way because the numbers are going to get weird. We got to square up our 7/20. We got to square up our 1/10. So we're going to end up with what? 50 times, what's that, 49/400 minus 1/100. And do you mind? Can I cheat? You going to make me write this again? Or can we just multiply by 4 top and bottom? And call it 4/400. Now it looks like we have 50 times, and 49 minus 4, I'm pretty sure is 45. And oh, look at that. That's nice, because we're using frickin' fractions. Well, 50 goes into 400 how many times? 8. So we ended up with 45/8 joules. But again, if you're pro with decimals by hand without a calculator, then you just write them as decimals. But I highly advise using fractions. But I know a lot of you will not listen to me because you're like, I'm at home and I have a calculator. I don't need that. Well, you might want to practice with it. Or not, do you? So there's Hooke's law. And if you want to get a little bit of practice, see if you got it down. Here's another one. Give it a shot. See if you can knock it out. It's essentially the same problem, just different numbers, different spring constant. Check it out. I'm not going to solve this one, but I thought I'd just throw it in for those of y'all nerds that want to check to make sure. So it's the same setup. It's the same game. It's all the same crap, just different numbers. All right. I'll see you in the next.